so far in this chapter on network measure, so we have discussed degree, degree distribution. We have also looked at different measures which are roughly divided into three buckets, right? Microscopic, macroscopic, and mesoscopic. We have seen metrics like clustering coefficient, local clustering coefficient, global clustering coefficient, and connected components, right? Strongly connected components, weakly connected components. So here we will discuss another very interesting aspect of network measure. It's called centrality. Now this is widely used, right? Centrality is basically a measure of how central a particular node is with respect to the network, right? So you can think of it, I mean, if I say that, to check whether a node is central to a particular network, so the first thing that comes to our mind is whether the node has equal distance to all the other nodes, right? Say if a node has equal distance to all the other nodes, more or less equal distance to all the other nodes, you can say that that node is basically a central node. But we are not talking about that kind of centrality here. We are talking about, of course, this is one aspect of centrality, but there are other notions of centralities. And remember, the notion of centrality depends on the particular application. Say if the application is, say, outlier detection, you have different notion of centrality. If the application is information spreading, you have another type of centrality. If the application is, vaccinate nodes, you have another type of centrality, and so on and so forth. So in general, when we talk about centrality, I generally look at it, using these four P's, right? So the first P is the prestige. We want to quantify prestige in the formulation of centrality. We will try to quantify prominence in the formulation of centrality. We quantify importance of a node in the formulation of centrality, and then power, okay? So these four P's are something that we will try to incorporate in the definition of a centrality, okay? So let's look at the first centrality, the basic one, the first centrality measure, which is called the degree centrality. So we know what is degree. Degree is basically the number of edges, adjacent number of edges which are incident on a particular node, right? So what is degree centrality? Degree centrality is essentially the degree of a node, but it is normalized, right? So degree centrality of a node V is the degree of the node V and divided by the maximum degree of a node present in the graph, right? You see the max degree, and that's the denominator. So for example, in this particular graph G1, if you look at say node 1, the degree centrality of node 1 would be 2 by the max degree is 3, right? So the max degree is 3 or 4, right? The max degree is 4. So this would be 2 by 4, okay? Degree centrality of node 3 is 4 by 4, and so on and so forth. So as you can understand, it basically ranges between 0 to 1, and the more the degree centrality, the higher the case that the higher the likelihood that the node has maximum degree, and therefore in certain applications, for example, say you want to identify a prominent node, or you want to identify celebrities, for example, right? And so in any application where you use degree as a measure, right, you can use degree centrality. That's a very simple notion of a centrality. The second one is called closeness centrality. Remember all these centrality measures that we are talking about here, these are all node centric properties, but of course you can map it to edge centric as well, right? So the next one is closeness centrality. So as the name suggests, we will look at how close a particular node is with respect to other nodes in the graph, and depending on that we define this closeness centrality. So closeness centrality of a node V is basically, you can basically say that let's look at the shortest path distance, right, of say distance of V from the remaining nodes u, where u belongs to the vertex set V minus the V itself, right? Because we will not measure the distance of V with respect to itself. So, with all the other nodes, what's the distance of V, and you just normalize it in some ways, right? If you do it, that is also okay, but the problem is that we also want that higher the value of centrality, better would be the node, right? Higher the value of closeness centrality, better would be the quality of the particular node. Say, think of a node, right, which is closer to all the other nodes. So, the sum of the distance would be lower compared to another node which is further, which is further from the other nodes, right. So, say let's say you have u and v. U is closer to all the remaining nodes, so the distance would be, the sum of the distance would be lower, whereas v is further from the other nodes, so the distance would be higher. Therefore, the closeness centrality value, forget about the denominator, you can use any denominator, right, I will discuss. So, irrespective of the denominator, the closeness centrality value would be higher for node v, because for node v the numerator value is higher, right. But that is not the desired output, right. We basically want that the node which is closer to the other nodes should have higher centrality values, right. So, how can we then do some sort of tweaks here in this particular formula? We actually reverse it, okay. So, closeness centrality is basically defined by the fraction where the denominator would be the sum of distance, okay, and the numerator would be the normalizing factor. So, in this case the normalizing factor is number of nodes minus 1, mod v minus 1. So, if you do this, in that case, lower the distance, lower the sum of distance, higher would be the centrality value. So, the node which is at the center position of a network, which has lower distance with the remaining nodes, that will have higher closeness centrality value, okay. So, using the closeness centrality, we can essentially identify nodes which are central to a particular network, right. What is the usage of this particular centrality measure? Now, think about it. So, I am basically trying to identify a node which has small distance with the other nodes, right. So, it means that if I want to spread, say for example, I want to spread a particular information to the entire network, okay. I would basically identify a node, right, which has higher closeness centrality, right. If I identify that node and if I convince that node to spread the information, it is highly likely that the information will spread across the network faster than the case where the node has lower closeness centrality values, okay. So, in case of say viral marketing or say spread of information, so spread of fake news, misinformation, right, in fact spread of say any sort of epidemics, right. So, you basically, I mean, from an adversarial point of view, think of it as an attacker. You are an attacker and you want to attack the network by spreading the fake news, misinformation. You basically choose nodes whose closeness centrality value is maximum, and you basically convince that node to spread misinformation, okay. So, now let us move to the, so I have already discussed I mean how to formulate closeness centrality. Let us take an example. So, let us say we have G1 as a graph, right, and let us look at the closeness centrality of node 1. So, node 1, if you look at the distance from 1 to 2 the distance is 1, from 1 to 3 the distance is 1, from, remember we are interested in shortest path distance, okay. We discussed what is shortest path distance in the last lecture. From 1 to 4 we have distance 2, this and this, right, and from 1 to 5 we have distance 2, right. So, the sum of the distance would be 6, total number of nodes is 5. So, 5 minus 5 minus 4 would be 5 minus 1 would be 4, so 4 by 6 you have 0.67, right? But what about 3? So 3 has distance 1 to all the other nodes, from 1, from 2, from 4, from 5, right? So you see the denominator is 4 and the numerator is also 4, therefore the closeness centrality of node 3 is 1, right? So you can also look at it manually, that 3 is basically at the center of the network, right? Therefore its closeness centrality is maximum. So if you want to spread certain information, you basically need to convince node 3, and if node 3 spreads some information or tweets something, right, immediately its one of neighbors will receive that information. Okay. Now let us look at the third notion of centrality, which is betweenness centrality. So this is very interesting. So as the name suggests, we will look at nodes for a particular node. We will basically look at possible paths and see whether that particular node is a part of the paths, right? So let's try to quantify it. So what we will do, we will take all pairs of nodes. There are in situ pairs. We take all pairs of nodes, and for every pair xy, for example, right, for every pair xy, we look at the shortest path. Now remember, there can be multiple shortest paths, right? The value of the shortest path will be unique, of course, but you can have multiple shortest paths. So for every pair xy, I will figure out the shortest paths, and I will see whether the particular node V, for which I am measuring the betweenness centrality, whether node V is present in how many of the shortest paths, right? Say between x and y there are 5 shortest paths, and out of these 5 shortest paths there are 3 shortest paths where the node V exists. These 3 shortest paths actually move through V, right? And that would give you the quantity. Now we will do this for all pairs of shortest paths, right? So let us assume that the sigma xy v is the, so let's first look at sigma xy. So sigma xy is the number of shortest paths between x and y, number of shortest paths between x and y, and I am interested in computing the betweenness centrality for node V. So out of all the shortest paths between x and y, right, how many shortest paths, in how many shortest paths this node V exists. So this sigma V xy indicates that out of all the shortest paths between x and y, in how many shortest paths between x and y the node V exists. Okay, and I basically do this for all pairs x comma y, which is a part of V cross V, for all pairs. Okay, now if now think about it, if a node has higher betweenness centrality, what does it mean? It means that the node is present in almost all the shortest paths between pairs in the network, right? So whatever path you want to choose, that particular node will always come, that particular node will always be encountered. What does it mean, and where this betweenness centrality would be useful? So think of a vaccination drive, right? So say an epidemic is going on, and you want to stop the spread of epidemic, so and you want to vaccinate certain nodes. Okay, now think of a network like this, right, like this. Okay, now think of this node, and let's assume that the epidemic has been detected in this part of the network, right? And the epidemic has already been detected, and you want that the epidemic should not flow from this part of the network to this part of the network. So what would you do? You basically vaccinate this node, because you know that this is the junction point, and if you vaccinate this node, right, the epidemic will not move from this part of the network to this part of the network. Okay. So if you compute the betweenness centrality of all the nodes in this particular graph, you will see that the betweenness centrality is maximum for this junction node, which is very obvious, because when you take all pairs, right, when you take one node from this component and one node from this component, you will have to move through this particular node, right. Now this kind of node is also useful for identifying clusters. Okay. Say for example, if you identify nodes which has higher betweenness centrality or the highest betweenness centrality, and if you remove that node, what would happen? You may see that the network would get disconnected. Say for example, in this case, if you remove this node, the adjacent edges will also be removed, right. So you will see there are two disconnected components emerging. So this betweenness centrality concept is also useful for the purpose of attacking a network. Say you want to decentralize a network. Now think of a terrorist network. So let's think of a terrorist network where nodes are terrorists and links are relations between terrorists, and you identify a node which basically acts a bridge between two terrorist organizations, right. If you break the node, if you kill the terrorist or if you arrest the terrorist, what would happen? The information that's flowing from one group to another group, that will be broken, that will be stopped, right. So these are some of the applications of betweenness centrality. Now this node whose betweenness centrality is maximum, this is also called articulation point. Articulation point. Now this terminology is very, very useful, right. So articulation point is a node whose removal will disconnect a particular network. Okay. It is not necessary that if you remove a node, it would disconnect the network, right. But let's say you have another edge like this. Okay. So if you disconnect this node, nothing would happen. The network will still remain connected. But at least what would happen is that your cluster would become prominent, okay, meaning that your inter-cluster edges, so these are inter-cluster edges, the inter-cluster edges will be reduced and intra-cluster edges will remain same. Therefore, the clustering structure will become prominent. Okay. So, and this is also useful for and this articulation points or the nodes with higher betweenness centrality, these nodes are also very dangerous. Why? Because say for example, you want that some of the information should not move from one component to another component, right. So, and these nodes would act as a spy, okay, because this is the only node which connects two different components in a network. So you should be very careful, from these nodes. You should not, you may not want to share critical information with this node. These are also called gatekeepers. Gatekeepers, articulation points. These terminologies are used in different applications, right? So let's take an example. So say this is G1, and what we are doing here, we are creating a matrix. This is a matrix, 5 cross 5 matrix. You have 5 nodes here, 5 nodes here, right? And a cell, say x bar y. This is basically used to indicate that. So what is y? Y is the let's look at this component. Okay, 0/1 means that there are two shortest paths between. There are one shortest path between. There is one shortest path between 1 and 2, and there is no shortest path between 1 and 2 where the particular node V exists. So I want to compute the betweenness centrality for node V, which is 3 in this case. There is no shortest path between 1 and 2 where the node 3 exists. Let's look at it. So between 1 and 2, you see that there is only one shortest path and 3 doesn't exist, right? Let's look at this one. Say between 2 and 4, between 2 and 4 you have this shortest path and you have this shortest path. Okay. So, among these two shortest paths, so therefore, this is 2, then the denominator is 2, and among these two shortest paths, in this shortest path which is 2, 3, 4, the node 3 exists. So, therefore, the numerator is 1, right. So, the fraction is 1 by 2, right. Similarly, we do the calculation for all pairs between 1 and 1, 1 and 2, 1 and 3 and so on and so forth, and then what we do, we basically take the sum. So, in this case 0 by 1 plus 0 by 1 plus 1 by 1 plus 1 by 2 plus 0 by 1, 0 by 1, sum of all the cells, and for node 3 it would be 4. Okay. So, this is betweenness centrality. So, sometimes we mix up the concept of betweenness centrality and closeness centrality. Think about it very carefully. These two metrics capture two different notions. Closeness centrality captures how close you are with respect to other nodes, whereas betweenness centrality indicates, you know, what's the likelihood that whenever I basically want to move from one node to another node, you will be encountered. Okay. So, you can't avoid the particular node in every shortest path distance calculation. Okay. There are two different notions. I hope you understand what I am trying to say. All right. So, now this betweenness centrality can also be computed for edges, right. So far we have computed betweenness centrality for a node, and you can easily extend it for edges because straightforward, right. So, now again you look at all shortest paths, all pairs of shortest paths, and see for a particular edge how many times that edge exists, right, in all pairs of shortest paths, and the calculation will remain same. There is another notion called flow betweenness centrality, right. So, in betweenness centrality we are only looking at the shortest path, shortest paths between two nodes. Sometimes you may not be able to move through shortest paths because it may happen that shortest paths are congested in some ways. You may not be able to use the shortest paths. You may want to use some other paths which may not be shortest path, but slightly longer, but that would still fulfill your purpose. So, in flow betweenness centrality, instead of looking at the shortest path, I would actually look at all possible paths between a node, right, between a pair of nodes. So, all possible paths between a pair of nodes, it's computationally expensive. Therefore, we generally do not calculate flow betweenness centrality, but for certain applications, right, we may want to calculate flow betweenness centrality. Okay. Now we are moving to a bit complicated centrality measures. So far we have looked at simple measures like distance, shortest path distance, and so on and so forth, degree. Now we are moving to to another notion which is called eigenvector centrality, and believe me or not, this eigenvector centrality is something based on which a series of centrality measures have been proposed. Okay. So, what is eigenvector centrality? So, eigenvector centrality says that when we measure the centrality of a node, you would also look at the other nodes which are linked to the given node. Say for example, so this is a network, right. You see that node E is linked to many other nodes in the network, okay. But node B is only linked to, node B is also linked to many other nodes, but node C is only linked to B, okay. And the size of every node indicates the prestige or centrality or eigenvector centrality. You see that node B has maximum size followed by C followed by E and so on and so forth, right. So, what it is saying is that when we measure the centrality of a node, you also look at other nodes which are actually pointing to this given node, and you derive the centrality of the given node based on the centralities of the other nodes. And the idea is that if I am pointed by some of the highly prestigious nodes, my prestige will automatically increase. Okay? In other words, say on Twitter, if I am followed by Shahrukh Khan, for example, or Amitabh Bachchan, automatically my follower count will increase. Doesn't matter whether the other users are following me or not. So if I am followed by some social media celebrities, my prestige will automatically increase, irrespective of whether others are following me or not. On the other hand, if you think of another user who is followed by many users, but their prestige is not that high, my prestige would not be that higher compared to the case where I am followed by a celebrity, for example. Okay, and this is a very important notion, and based on that, a series of metrics have been proposed. I will discuss a few in the later slides. Right. So essentially, you see that the eigenvector centrality measure is a kind of a recursive approach, right? So I am measuring the centrality of a node based on the centrality of other nodes. So I will measure the centrality of the other nodes based on the centrality of their followers, all right, their neighbors, and so on and so forth. So it's kind of a recursive definition. Okay, so now let's move to the definition, right? What it is saying is that a centrality of a node, the eigenvector centrality of a node V is the sum of the eigenvector centrality of all its neighbors. So NV is the neighbors of V, set of neighbors of V, and T is one of such neighbor. So So xt is the eigenvector centrality of T. So I am taking the sum of eigenvector centrality of all the neighbors, right? And I am actually using some sort of normalization, say some sort of constant, say this is lambda 1. Okay, so this is the formula. Now you can write it in a different manner. You can say that, okay, 1 by lambda 1 sum of all the nodes present in V. How do I know that the T is a neighbor of this V, right? So I can use the entry in the adjacency matrix. So AVT, now think of it. So A is the adjacency matrix, okay, and one such entry is small a VT, small a such sub VT. So say this is Vth row and Tth column. So this would be either 1 or 0. If V and T are connected, then it would be 1, otherwise 0. Okay, so this times xt. If this would be 0, then this will not be considered. If this would be 1, then xt will be considered, right? So now you can see that I can write it in the matrix form. I can say that this is, so let me adjust this equation in some other ways. Let me move this lambda 1 here. So it would be xv lambda 1 equals to sum of, right, a vt xt, right? Now let's make it compact. So xv is the eigenvector centrality of node V, xt is the eigenvector centrality of node T. Let's assume that I have a 1D matrix X, where we have elements x0, x1, x2, dot dot dot, xv, xt, everything. So all these entries indicate eigenvector centralities of different nodes, and I have this adjacency matrix A, right? So can I write it in this manner, right? Say lambda 1 x equals to a x. So this is basically A and this is x. So you see this is the equation Ax equals to lambda 1 x. And if you know matrix operation, right, linear algebra, you should have heard about something called eigenvalues and eigenvectors, right? So this is exactly eigenvalue eigenvector formula, right, equation. So we know that this is the equation, right, Ax equals to lambda x. This is the eigenvalue eigenvector equation, right? So if you do not know what is eigenvalue, eigenvector, you go back and check, but roughly what it is saying is that, you know, so let me you know, briefly talk about matrix multiplication. I know this is not a linear algebra course, but let's briefly talk about it, right? So A is a matrix and X is a vector, okay? So now in a 2D space or a 3D space, right, x is basically an equation of say let's take a 2D, right, something like this. So you can think of x as an equation of I mean as a data point here, as a vector here, right, a 2D point. So when we multiply a vector with a matrix, what actually happens? It basically makes a linear projection or linear transformation, okay? So when you multiply this by a matrix, you get another vector, say y. So y is the linear transformation of x, right, and this transformation happens due to A, okay? Now this linear transformation, so what actually this you know, matrix indicate? So if you think of these columns of this matrix A, right, these are basically different, you know, basis vectors in your transform space. If you do not know what is basis vector, please go back and check. You are transforming now in a normal Euclidean space or coordinate geometry. We have two basis vectors, I hat, right, and j hat, right, which is 1 0 and 0 1. These are two basis vectors, right? Any vector can be generated based on these basis vectors. So when we multiply x with A, as if A matrix is transforming x to another space, right, where you have two different basis vectors, and these basis vectors are basically the columns of A, okay? So during the transformation, after the transformation, you will get a transformed vector y. Now what is special about this one? This is also transformation Ax equals to lambda x. So you are multiplying x with A, and the transformed vector itself is basically x, the same vector. So this is a special type of transformation, okay? And what is lambda? Lambda is a constant, okay? So lambda indicates whether the transformed vector is squeezed or expanded, right? If it is greater than 1, then you basically expand it. If it is a fraction, right, say 0.1 or 0.3, whatever, you basically squeeze it. It can also be negative, by the way. Negative means you are changing the direction of the resultant vector, okay? So this is a special kind of matrix linear transformation where the resultant vector actually resides on the span of the vector itself. Now what is span? Again go back and check the term span, right, basis vector. These are very important concepts, right? So I am not going into the details of eigenvector, eigenvalue concepts, but what it basically does in this particular case, you see that essentially x, which is the eigenvector, the eigenvector, right, of A. So this actually captures all the eigenvector centralities, okay? Now you may have multiple eigenvectors, eigenvalues. There can be multiple such transformations. There can be multiple such vectors which when you multiply with A, the vector will remain same with some constants, constant lambda 1, lambda 2. So which eigenvector, eigenvalue I should consider? So this is called eigenvector, this is eigenvalue, right? So it turned out that I should consider the principal eigenvector. I should consider the principal eigenvector. What is principal eigenvector? Principal eigenvector is eigenvector corresponding to the largest eigenvalue. So you will have multiple such eigenvalues. lambda 1, lambda 2, lambda 3 dot dot, right. So, you choose the maximum eigenvalue and you take the corresponding eigenvector, right. Why so? Your question would be, why we suddenly need to consider the principal eigenvector? Because what I wanted to do is that I wanted to come up with a vector, an eigenvector which is whose values are non-negative, right. I want to come up with a eigenvector whose values are non-negative. So, how do I guarantee that which eigenvalue I should consider, so that my eigenvector, all the entries in the eigenvector should be non-negative, right. There is a very nice theorem called Betweenness theorem, right, which basically says that if you want to identify an eigenvector whose all elements are non-negative, you should choose eigenvalue which is the maximum, right. So, therefore, I want to choose the principal eigenvector, right, of A. What is A? A is the adjacency matrix. So, it is a very simple thing, although the idea is a little bit complicated, but I mean the formulation is very simple. I have the adjacency matrix, I will get the principal eigenvector of the adjacency matrix, and each element in the principal eigenvector indicates the eigenvector centrality of the corresponding node. Okay. So, again, if you do not know how to calculate eigenvector eigenvalues, go back and look at some fundamentals on matrix operation. Okay. So I stop here. The next part of the lecture, again, that would be a continuation of this chapter. I will discuss about other variations of eigenvector centrality. I will discuss about page rank, card centrality, and so on and so forth. Thanks.